Hi, ladies and gentlemen. Here I am. It's April 5th. It's on a Sunday, so you're probably watching this tomorrow, Monday. If not, tonight, probably. I don't know. Some of you guys like to get a jump on things. I hope everybody's had a good weekend. I hope everybody's staying happy, healthy, staying busy. And yeah, let's jump right in. All right. So, you probably already have seen it in the intro video, but we're going to be talking about all of section 8 for this week. Okay. We're going to have day 1, which is this lesson, and then day 2, which is the next lesson. So let's just jump right in. Okay. Section. Oh, let me get this out of the way. Yeah. Okay. All right. Okay. So in the last quiz, we talked about what a rational equation is, right? And how to add, subtract, multiply, divide them, right? We've done all the operations with them. And we've taken a look at basic graphing of them. Section 8.4 and Section 8.5 are really going to get into the graphing piece of it, okay? And the solving piece of it, solving equations in it. Section 8.4 is really the graphing part. Section 8.5 is really the solving equations and inequalities part. Okay, so this week, we're going to be talking about graphing rational functions. Now, what is a rational function? A rational function is a function whose rule can be written as a ratio of two polynomials. That's what a rational number is, right? It's a ratio of two numbers, so a rational function is a ratio of two polynomials. The parent function is f of x equal to 1 over x. That's the parent, okay? 1 over x, just the number 1 divided by x. That's the inverse variation with k value of 1. Its graph is a hyperbola. Now, we've heard of parabolas before. Okay, we've heard of parabolas. This is a hyperbola. Okay, we've seen it. We've graphed it already. It's an inverse variation. We just haven't called it a hyperbola yet. It's basically just two separate branches, like what we've seen. Well, I guess it's down here. I'll just show this one. Okay, like this one. This is an example of a hyperbola. Right? Has these two separate branches, one on this side and one on this side. You will learn more about the hyperbolas in Chapter 10. Just kidding. We don't cover Chapter 10, especially not now. You're going to talk a lot more about that in pre-calc when you talk about conic sections. Okay. Now, like logarithmic and exponential functions, these have asymptotes. Okay, they have asymptotes. They have a horizontal asymptote. They have vertical asymptotes. They could have horizontals. They could have verticals. You don't really know. Okay. The function f of x is equal to 1 over x has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So it's got two asymptotes. One, the vertical one going along the y-axis, the horizontal one going along the x-axis. So this would be considered the line x equals 0, and this is considered the line y equals 0. Right? All right. Okay, so what are we going to do with these things? Well, we're going to transform them. Now, the transformations are not going to be as involved as they usually are. Okay. Basically, I'm going to give you this equation, and that's going to be it. That's the really transformations that I've gotten. So why don't you pause and write this down? Okay. So when I change this number on top, this a value, okay, when I change that number, move it away from 1, that is a vertical stretch or compression. Stretch. Vertical, again, is straightforward. So if it's a stretch, it's bigger than 1. If it's a reflection, then if it's a stretch, it's bigger than 1. If it's a compression, it's less than 1. Okay. Why is that the case? Because if I take 3 times 1 over x, who's texting? If I have 3 times 1 over x, right, that's just going to multiply up to the top. So 3 over x. So multiplication on the outside, which is normally a vertical stretch. I'm going to turn that off. Vertical stretch, that's just going to move up to the numerator. That's why if I change the a value, that's a vertical stretch or compression. Okay. So that would be a vertical stretch by 3. Now, if I add or subtract, those are going to be the shifts, right? So if I add or subtract at the bottom, that's a horizontal translation. I'm changing what's inside the x value. So if I make it an x minus 1, it's actually going to go to the right one. If it's an x plus 4, it's going to move to the left 4, just like all horizontal things would have done before. And then this k value here, that's obviously the one that moves up and down, the k value, okay? Which makes sense. It's always been that number sitting outside on the end. Still, think way back to like y is equal to 3x plus 2. That was your up to, right? The number sitting out with a plus or minus sign on the end is a vertical translation. Same thing here. Okay. So using the graph of 1 over x as a guide, describe the transformation and then graph the function. All right. So a couple things that I notice here. There has not been a vertical stretch or compression applied. Okay, the only thing that's happening is this +2. And that +2 is moving it to the left 2 units. Is it moving up or down any? No, because you've got a plus 0 there. So what does that mean? Well, that means that the whole normal hyperbola that we had, the 1/x, that was centered around the origin, just shifts to the left 2. So the horizontal asymptote does not change. The horizontal asymptote does not change, but the vertical asymptote does. It moves left 2 units. Okay, so here is my new boundary line. Think of this as my new, this yellow dot that I have in here. Think of that as my new origin point. Right. So that means that when I go to graph this, and again, this is talking in generalities here, it's going to look something generally like this. Just doing the best I can with this tablet here. Okay. That's generally what it's going to look like. Do I need you to go in and actually plug in values? No, I'm okay with that. I know you have your graphing calculators anyway, so you could just put it in your graphing calculator and see what it's going to look like. It'd be good to verify to make sure that it is looking like that. But, here's what I'm looking for. I'm looking for, where is this new origin point? Did you have that in the right spot? Are you having the vertical and the horizontal asymptotes in the correct spot? That's what I'm looking for there, okay? And generally is in the right spot. Did you accidentally put it up here or something like that? Don't do that. Right? Don't do that. Okay. So let's take a look at the next one. Get a pen. The values of h and k. Oops, I didn't need to go that far. I want to go here. Okay. So again, no vertical stretch or compression applied. I'm going down 3 units. And I'm not going left or right any. Okay, so now my vertical asymptote does not change, but my horizontal one goes down 3 units. Okay, so now this yellow dot here is my new origin point. Again, that's not part of my graph at all. That's not part of my equation at all. I'm just putting it there as reference. Okay. So there's my new hyperbola. Okay. Again, just sketching it. I'm not looking for exactness here. Okay. All right, so getting back to this. The values of h and k affect the locations of the asymptotes, right? Obviously, shifting it up or down, left or right are obviously going to change where the asymptotes lie. So what are the rules? How do we summarize that? H and k affect the locations of the asymptote, and they also affect the domain and the range of the rational functions whose graphs are hyperbolas. So in summary, again, I'd go ahead and pause and write that down. Okay, so we know the graph is a hyperbola. Okay. There is a vertical asymptote. Well, what changes a vertical asymptote? Well, that would be pushing it left or right. So that means the h value is where the vertical asymptote is. The domain, therefore, means all x values such that x cannot be h, which makes sense. Think about it. If I asked you for this function up here, what is undefined? Well, what is undefined when the denominator equals 0? So an h right here, that would make the denominator equal to 0. So x cannot be h, right? So that's my domain. Now, what's my range then? Well, the horizontal asymptote is y equals k. Y equals k, because that's what's both shifted up and down. Right? Y equals the up and down motion. And then the range is all y is such that y is not k. Okay, so there's my k value in there. Okay, no pun intended. All right, identify the asymptotes, the domain, and the range. All right, so it looks like I'm not graphing here. Hopefully not. Do I see a graph there? No. Okay, so identify the asymptotes, the domain, and range. Now you're going to see me abbreviate horizontal asymptote as HA and the vertical asymptote as VA. And we'll do the domain and we'll do the range here. All right, so where is the horizontal asymptote? Well, the horizontal asymptote is always the equation y equals something, right? So what is it? Y equals k, -2. Vertical asymptote, what makes this function undefined? When x is -3. Right? Okay, if I plugged in -3 in here, that would make it cancel, giving us a 0 down here on the bottom, which is no good. Right? That's what makes that function undefined. Now, the domain. Actually, I should have rewritten this. probably should have that flip-flopped around because the vertical asymptote matches right up with the domain, which is all x values such that x cannot be -3. And then the range matches up with the horizontal asymptote, all y's such that y cannot be -2. Okay. Oops, forgot to put the caps on the end. All right, there we go. Okay. Oops. Okay. Okay, so this one, let's say the vertical asymptote first, and then do the horizontal asymptote. Okay, the vertical asymptote again is an x equals, what is it in this case? X equals, isn't it just 3? Oh, it was -3. It's +3 this time. The horizontal asymptote is y equals -5. That one's straightforward. This is the opposite of what's there. That's straightforward. All right, so that means the domain is all x values such that x cannot be 3. And the range is all y values such that, ooh, that's a really good brace there, isn't it? Y cannot be -5. All right. Okay, again, these should match up. The vertical asymptote and the domain should match, and then the horizontal asymptote and the range should match. Okay. Uh-oh. Kid's got to go potty. I'm going to pause the video. Hold on. Okay, and we're back. Sorry about that. So I think I was saying something about the vertical asymptote matching up directly with the domain and the horizontal asymptote matching up with the range. So I think we're good. All right. Now, there's this idea of continuous versus discontinuous functions. Okay. Really, why are we bringing this up now? Well, basically because the graph of a hyperbola is really the first discontinuous function that we've done. Okay, it's like our very first. I think it is. I don't think we've done any other discontinuous functions. Now, what does that mean? That means that there's a gap or a break. Okay, that means there's a gap or a break. As noticed by, where's my pen? Let me move this down. I'm going to draw real quick. You know, if I draw just a quick hyperbola here, we notice that there are no, like this is all undefined in here, right? You know, I know that I kind of went over here and that's defined up there, but there's this middle piece where nothing is defined. That means as I move from left to right that there is a gap, there is a break within this function. This function is what's called discontinuous. There is a discontinuity there. Okay. Every other function that we've done so far has been continuous. Now I know we've had asymptotes before, you know, thinking about like the logarithmic function, looking something like that. And, you know, all over here was undefined. But did this ever break? No. It didn't break. It was just, there was nothing over here. It was still continuous. Okay. I never had to like pick up my pencil and keep drawing on another spot of the graph. Okay. So this is our first discontinuous graph. A continuous function is one that has no gaps or breaks, like everything that we've studied so far. Linear, quadratic, polynomial, exponential, logarithmic, they're all continuous functions. Now, you know, we're not really learning too much about what that means. What are the implications of that? I think you can get more into that in pre-calc and calculus, and because there are certain things, certain implications if it's discontinuous or continuous. Okay. It's just interesting to bring up right now. The graphs of some rational functions are not hyperbolas. Consider this rational function. Okay, now what's going on here? You know, this is a rational function. Obviously, if I multiply this out, there's a big polynomial on top and then a polynomial on the bottom. But it's still a rational function, and it still has some of the same properties. Okay, now take a look at what's happening here. The numerator of the function is 0 when x is 3 or -2. Right, we would all agree with that. If x is 3, then this whole top turns to 0. If x is -2, this whole top turns to 0. And when the whole top turns to 0, 0 divided by anything is always 0. So you could say that the zeros of the function are -2 and +3. The x-intercepts are -2 and +3. But there's a point on here where this function is undefined. If I set that equal to 0 and -1, this function is undefined at -1. So what does that mean? That means that there's actually a vertical asymptote at -1. This is the equation. This is the function that looks like, and it's a graph. Notice that the y-intercept, or sorry, the x-intercept at -2 and +3. And we've got the vertical asymptote at -1. Okay? So, to summarize, if you've got any polynomial rational function with a polynomial on top and a polynomial on bottom, that's the notation there. P of x on top, Q of x on bottom. Now, the function has zeros at each real value where the top equals 0. That's where the zeros are. Okay? The bottom is where your vertical asymptotes are. The bottom equaling 0 is where your vertical asymptotes are. Now, in the second day of section 8.4, that's when we're going to get into horizontal asymptotes, but vertical asymptotes. That's what we're going to be looking at here. Okay. So numerator zeros are where the zeros of the whole function are. The denominator zeros are where the vertical asymptotes are. Okay. So let's take a look here. Identify zeros and vertical asymptotes of the function. Then we're going to graph, and I'll probably use my graphing calculator to help us out a little bit. All right, so the zeros of the function. The zeros are where the numerator gets set equal to 0. Okay. Hold on just one second. I think I have to pause again. My kid is back. Okay, I think I'm back now. Okay, so I was here with the zeros of this function. Now again, the zeros of the function where the numerator equals 0. So we will factor this down. Factors of -4 that had to get to +3 are a +4 and a -1, right? So we're still setting that equal to 0. So x plus 4 equals 0 and x minus 1 equals 0. So x equals -4, x equals +1. So the zeros are -4 comma 0 and 1 comma 0. Okay, however you want to write them. I like to write them as ordered pairs, but that's up to you. Okay, now next thing I want to do. I want to find where the where the vertical asymptote is. The vertical asymptote lies again where the denominator equals 0. Right? So it's x equals -3, which again coincidentally says, when is this function undefined? This function is undefined at x equals -3. So again, if I wanted to make a crude sketch of this vertical asymptote at -3, -1, -2, -3. Ooh, let's not make it a curve there. Okay, so vertical asymptote at -3. Okay, doing my best there. And then I know that it has 2 zeros, one at 1 and the other one at -4. Okay, so now I don't know whether this dives down or whether it dives up. I'm not really sure. So at that point, I'm just going to go to my calculator, and I am going to plug that in. Get my plot off there. Okay, so we're going to put in there, again, I think it was x squared plus 3x minus 4 on the top, and then on the bottom, x plus 3. Always put your numerators and denominators in parentheses when you're going to graph them in your calculator. So I'm going to zoom 6 this. Okay, it looks like it's diving up here and then around there. Okay, so I'm just going to copy this screen here. So to sketch it onto my paper, looks like it's going to go up in through here and then down and bend here. Okay, there you have it. All right, let's do one more. Okay, so the numerator, again, if I want to find the zeros of the function, the numerator, again, -3. Why do I have x plus 3's in my denominators, both of them? My zeros are where the numerator is 0. Right? So I say, okay, this factors into x plus 6 and x plus 1. So x equals -6 and x equals -1. My vertical asymptote is x plus 3 equals 0. So x equals -3. That's my vertical asymptote. It's where the function is undefined. So what does that mean in terms of my graph? That means that I've got another vertical asymptote at -3, just like the last problem. And then I know I have zeros at -1. Actually, I'm going to change colors here. -1 and -6. 4, -5, -6 here. Okay, and at that point, I'm going to go to my calculator and plug this in. So I go x squared, it looks like plus 7x plus 6. Then over x plus 3. So we'll graph that. Looks like it's diving up here. And then up from the bottom here, which makes sense. Okay, somewhere over there. Okay. So I hope we all enjoyed this video. Sorry for all the interruptions, and I'll be back with the next one.